Hello everyone, today we'll talk about the solution to the problem lexicographical numbers. Here we want to generate all the numbers from 1 to n inclusive and sort them in lexicographical order. So not the standard sorting 1, 2, 3, 4 and so on, but we sort them as if they were strings. So for those who are unfamiliar with lexicographical or dictionary or alphabetical sorting, it's when you have A and B that you want to compare, then if A is a prefix of B, then A is smaller than B. Otherwise, if neither A is a prefix of B nor B is a prefix of A, they differ at some position, and at earliest position, leftmost position where they differ, so let's say we have 1, 2, 3, 1, 2, 3, and now here we have a 6 and here we have a 9, then we look at the first position where they differ, and that position defines for us which is earlier lexicographically. So we just compare those two characters. And of course, the easiest solution would be to just sort the values as strings, but that would give us an n log n solution. So we want a solution that has linear time and constant extra space, because of course we have to generate the list of numbers, so that's linear space, but we want to do it specifically in linear time. And to solve this problem in linear time, we should actually look at what the final answer will look like, how it'll start, and what the rules for generating it are. Because we know that we'll always start with a 1. 1 is lexicographically the smallest value because it starts with the smallest digit, and is the shortest that it can be. And then we'll have 10, 100, 1000 and so on. Of course, up to the limit. We cannot exceed the limit. And let's say that 1000 exceeds the limit, but 100 doesn't, and 101 also doesn't, 102 also doesn't. So those are the next values. Let's go up until 109. All of those, let's say, are under the limit. And so the next value is not 110, but it is 110 without the final digit, so it is 11. Then it is 110, and then 111, 112, and so on. So we can see that whenever we have the final digit that is not equal to a 9, so that we can increment it, right? Increase it by 1 without changing the rest of the number, so this prefix, then we just increment it by 1, that's the next number in order. And now, if there is a 9, that means that after incrementing that 9, we'll get a 0, which we can remove, get a shorter number. And of course, if the number is 199, let's say, then after incrementing we get 200, but we should remove both those zeros and we get just 2. Then we get 20, then we get 200, and so on. So we keep adding zeros for as long as possible. If it's no longer possible to add zeros, we increment the last digit. If it's no longer possible to increment the last digit because it's either equal to a 9, so it will change the rest of the number, or the resulting number is bigger than the limit, we have to remove the last digit and try to increment from what remains. So this is essentially the basis of the solution, to observe the process, observe the patterns, and now we just have to implement it. So again, we start with 1, and at every step, we of course append our number, and we try to multiply it by 10. If it's okay, if it's still below the limit, then we can continue. That's equal to this pattern of 1, 10, 100, and so on, then 2, 20, 200, and so on. Then, if it's no longer possible to add a 0 to the end, then we have to make sure that the number is not greater than the limit. And of course, also that, here we have greater than or equal, because at the end we're going to add 1 to the number to get a new number that we haven't seen previously. So the number cannot be equal to our limit, it has to be smaller than our limit, because after adding it should be less than or equal to the limit. And of course, if the final digit is 9, we cannot just simply add 1, because then we have this 0 that we'll have to get rid of. And to simulate getting rid of that 0, we get rid of that 9. So both of those situations will have to remove the final digit of our number. Then we increment it, and at the end we have, of course we do it for n steps, because we know that we expect n numbers on our list, and those will be the numbers from 1 to n. and at the end we return the final result.